kind of a nice fact. Let me give you another fact. I'm not going to prove this one right now. These are just by the way, these are helpful things. Like let's say you know 2 of your 3 eigenvalues, but you also know the determinant of the matrix. Well, then you can find the third one. Okay. Here's another equation. The trace of a matrix. You guys remember what the trace is? It's just the diagonal entries added together. Turns out that the trace of a matrix is the sum of the lambdas. So you add up the lambda values, you'll get the trace. That's actually easy. It's very easy to calculate the trace. You just look at the main diagonal and add up the numbers. It's just the sum of the eigenvalues. So between these 2 equations together, you can actually get a lot of mileage on figuring out what your eigenvalues are. Okay. So that's good. Okay, I've got a couple more, let's see, I've got a few more problems. I'm going to try and do them in order of what I think might be most important here.
So we decided that T
it's not diagonalizable. And if it was diagonalizable, our Jordan canonical form would have been a bunch of 1 by 1 blocks. But it wasn't. It was one single large block. And so that means it's not diagonalizable. This eigenvalue up here had a very high multiplicity, but didn't pull its weight. It only gave us one linearly independent eigenvector. That make sense? Okay. This next problem I really, really like. Let me do it. Got like a couple more here that are a little longer, and then I might throw a couple things at the end. It's already 6:15. Wow. Definitely going to get this done by 7. You don't have to stay that long if you don't have the time, but I think these are nice problems. You can always watch them on the video later if you can't stay late, so don't worry about it too much. But here's what I'm going to do. I'm going to let P be the plane 2x minus y plus 3z equals 0. And then I'm going to assume that T from R3 to R3 reflects points over the plane P. So we're going to reflect the points across the plane P. So then here is the question. Find T of ABC. So I want a formula for this linear transformation. So here's your, your R3. And somewhere in there you've got this plane. It's very hard to draw. So there's a plane there somehow. And what we're going to do is, this is like the 3-dimensional version of flipping across a line in the 2-dimensional plane, in the XY plane. Now we're doing XYZ. But basically, if we take any point that is kind of over here, so we take, XYZ, we're going to transform it by pushing it across the plane to T of XYZ. You're just flipping it straight across. It's not the greatest picture in the world. If you looked at the plane sort of from the edge on, then this point XYZ would be getting moved over here to T of XYZ. Right? So you'd be flipping it literally across that plane. Okay. So that's the problem. Can we come up with the formula for that? Does anybody know how I might want to start on that?
I know we get to use the schematic.
We get to use what? Yeah, the schematic. Yeah, it's going to come in there. That Theorem 2.14 diagram that I did in the recap. Yeah, that's definitely a part of this.
Should we find the normal vector?
Yeah, the normal vector for the plane would be helpful. So for the solution, so the plane is 2x minus y plus 3z equals 0. normal vector, this is the perpendicular vector. Does anybody know how to find a normal vector for a plane?
You need to take the cross product of 2 points that are on the plane. 2 vectors.
Even simpler than that. If I've actually given you the equation of the plane,
You just have to pick the point that's on the x-axis equation.
well, that'll give you points on the plane. That's what Davey was saying. I'm saying it's easier than that. If I give you the equation of a plane, let's make our map 250A instructors proud. So ax plus by plus cz equals 0. What's the normal vector?
It's just the problem.
It's just these numbers, right? 2, negative 1, 3. Perfect. Okay, so that's my normal vector. 2, negative 1, 3. Now the thing about the normal vector, okay, see this is actually a very good point. So if this is normal vector's perpendicular, I'm looking at the edge on view. So this is a whole plane here, right? Coming straight out at me. This is my normal vector, which is 2, negative 1, 3, right? Where's it going to get transformed to? It's going to flip over there, right? Would you agree that it's going to be an eigenvector? Right? In fact, what we know, what hopefully you can tell, is that 2, negative 1, 3 is going to get transformed to negative 2, 1, negative 3. It just gets flipped exactly the opposite side of the origin. Okay, so let me just be clear. If this is 0, 0, 0 right here, and which by the way is on the plane. So 0, 0, 0 is on the plane. Here is the normal vector, 2, negative 1, 3. So when you transform it, it comes over here and it's negative 1, negative 2, 1, negative 3. Notice the origin is sort of the midpoint between these two. So the origin right in the middle, the difference between these two are just changing the signs. Okay, so in some sense, that's a good vector to transform. So here's the problem, guys. We're trying to figure out how to transform an arbitrary point. That maybe seems hard, but here at least we found one point that we could transform easily. Okay? Could we find any other points that we could transform easily? Yeah, if I start with a point on the plane, say down here somewhere, where's it going to get transformed? To itself. Doesn't move, does it? It stays right where it was. If you're flipping points, it's just like with the line, right? If you flip points across this line, then any point that's on the line stays on the line. It just doesn't move, right? So we need some points that are on the plane, and for the benefit of making this problem not become a disaster later, would you allow me to pick some points? There are many points that you could pick, but see, I have notes that are well worked out for specific points, so I really appreciate if I could choose them. Okay, so points on the plane. Okay, so would you agree that 2, negative 1, negative 1 is on the plane? Let's see if that seems reasonable. 2, negative 1, negative 1. Is that all right? And another point that would be on the plane that I wrote down was 0, 3, 1. So 0, 3, 1 hopefully is also on the plane. These points are on the plane. And the point here, guys, is that when you transform either one of those points, if you transform a point that's on the plane, it doesn't move. Now, yeah, Joseph, go ahead. I'm about to make another comment that you might jump.
That should be 2, 1, negative 1. No?
No. It should be 2, negative 1, negative 1.
That would be
Oh, it's because you have negative 1.
Oh, I'm sorry. 2.
One.
Oh no. 2, 1, negative 1. That'd be here. Oh, good lord. Oh no. It's gonna mess up this whole thing. Does anybody have a calculator on by chance? Maybe if somebody has a calculator, I might be able to rescue it. So it should have been 2, 1, negative 1. Screw that up. Okay. I may or may not. I'm not going to worry about the calculator part too much. Obviously, you're not going to have a calculator on the test either, so surely I can do this without that. So the point is that 2, 1, negative 1, that was silly of me to make that error. But anyway, those are the points that are on the plane. These are notes I wrote years ago. I'm much smarter than that now. Now, I chose these, so what do you suppose I would like to be able to say about those 3 points that I had chosen now?
On a basis.
That they form a basis for R3. I would love to make that into beta. I mean, notice, for example, I didn't choose 0, 3, 1 and 0, 6, 2. Now, that would not be very helpful, even though those would be 2 points on the plane. I don't want to choose 2 points. See, the plane is two-dimensional, so I can pick 2 points that are on the plane that are not linearly dependent. These are going to be linearly independent. By the way, I know that without even checking it. Think about it. Are these 2 multiples of each other? No. And they lie within the plane P. If I add a 3rd point, I'll think of the top one as the 3rd point. If I add a 3rd point that is not already in the span of the first 2 points, and I enlarge my set by doing that, my new set stays Li. So these 3 vectors must form a basis. They are linearly independent. And so let me write them down as a basis. So we get a basis. I am going to call this basis beta prime, which is the basis 2, 1, negative 1, followed by 0, 3, 1, followed by 2, negative 1, 3. There's my basis beta prime. And I already know, very simply, I already know the matrix representation of T relative to beta prime, don't I? Because all it is I just take my, what do? I take my vectors, I transform them, and I rewrite the results in terms of the same basis again. Well, if I take this first vector and I transform it, I get the same thing back again. And with respect to this basis, what's the coordinate vector of 2, 1, negative 1 relative to this basis? 1, 0, and 0. Right? Remember, what are you doing? You're taking 2, 1, negative 1 and writing it as a linear combination of these 3. It's going to be 1 times this one, plus 0 times this one, plus 0 times this one. And those 3 coefficients, the 1, the 0, and the 0, go right here. Agreed? I'm just making sure because I'm not sure everybody's quite happy yet.
I guess I don't understand why when we transform the first points, the 2, negative 1, 3, we got negative 2, 1, negative 3, and then we transform the other 2, we didn't.
It's because of the geometry of it. If I start with points that are on the plane and I transform them, they don't move.
Okay.
They stay the same. There's no change. But if I start with a point that is perpendicular to my plane, normal vector, and I flip that across the plane, reflect it across the plane, then it goes 180 degrees opposite in the other direction, which essentially means every single coordinate picks up a minus sign.
Okay.
Does that make sense? Okay. So let me ask you guys about the second vector. When I transform 0, 3, 1, I get 0, 3, 1. I rewrite that in terms of the basis, and I get 0, 1, 0, right? What about 2, negative 1, 3?
Negative.
0, 0, negative 1, right? The idea, guys, is this is an easy one. That's easy to find that thing. What I really want to find, however, is if I take the standard basis, I'm going to call it beta, which is a standard basis 1, 0, 0, 0, 1, 0, and 0, 0, 1, I really want to know, I really want to know T with respect to that basis, right? Because here's why. The reason I want to know T with respect to this basis rather than this basis is because if I want to answer the question of what is T of ABC, ABC is really a coordinate vector ABC with respect to beta, the new basis, right? So I'm just going to take, if I want to know t of ABC, all I'm going to have to do, this is the schematic that we're talking about, all I'm going to have to do is take ABC, write its coordinate vector with respect to beta, which will be ABC, apply the matrix to it, which we don't have yet, get an answer, which will be another column vector, and then take that column vector and write it as a linear, basically, that's a coordinate vector for t of ABC. Then you can write down what t of ABC is. Does that make sense? Let me sort of outline what we're going to do right here. I'll actually write it down. Might be helpful. Okay? Let's draw the schematic for this particular problem. We're starting with ABC. We would like to come over here and transform it. This is what we want. So the way we're going to do that is we're going to start by going to the coordinate vector, which is ABC. Now that's with respect to beta, right? Actually, let's start it this way. That column right there, that is just ABC with respect to beta. Then what I'm going to do is I'm going to multiply by t with respect to beta, which we don't have yet. And I'm going to come over here and I'm going to get the coordinate vector of t of ABC with respect to, well, it's the same basis, beta again. This is beta to beta, right? I'm going to get this coordinate vector, then I'm going to go back up to find out what t of ABC is. This making sense? So this is the schematic. In order to use the schematic, I have to have this matrix. So we're going to need to change the coordinates. So we have this matrix, but we want this matrix. Do any bells go off as to what relates those two matrices? They're similar, and we actually have a way of going between them, right? This is the theorem 2.23. This is the one, I know I'm not expecting you to know the numbers, but the formula is that t with respect to beta prime is just q inverse times t with respect to beta times q. And let's just remember what q is. Where q is the change of coordinates matrix, the identity transformation from beta prime to beta. Make some sense? Okay, so now of course, actually in this case, I actually want t sub beta. So if I actually need to take this equation and solve it for t sub beta. So t with respect to beta is actually going to have the q on the left side, and then t with respect to beta prime, and then q inverse, just the way I've set it up here. It's really not a big deal though. I've already got this matrix. I need to get q and q inverse. Which one is easier to figure out right now? The q or the q inverse? Nice to ugly or ugly to nice? Ugly to nice is what we want. Which one's ugly? Beta prime. Which one's nice? Beta. So actually, this q is an easy one to find, right? This one. So what is it here? Let's come back to this thing. So what do? We take the beta prime basis, we do nothing to it, and then we write the result in terms of beta. So I take beta prime, the first vector, I do nothing to it, 2, 1, negative 1, I write it in terms of that, and I'm going to get, well, 2, 1, negative 1, right? It goes in the first column. So we're going to get 2, 1, negative 1. Agreed? Then I got to do the same thing with the second vector, which is going to be 0, 3, 1. And then I've got to do the same thing with the third vector, which is 2, negative 1, 3. So that's q. So far, so good? Okay. And now we get to the very sad moment. Nobody found a calculator, is that right? Do you possibly have a way of calculating the, boy, do I really want to do that, because then I'm going to have to make you do this calculation. See, my Q inverse is going to be wrong, because I had two -1, 1, -1 here. Gosh, what am I? Let's do this. Let me just make up an answer. Okay, so we know what Q is. We know what T sub beta prime is. Let's suppose we could find the inverse. It's a 3 by 3. It's not going to be simple. So let's just make up something that's reasonable here. Okay, and it may not be correct now that I realize my notes had the wrong vector there. I got 2/3, 1/3, -1, and then 1/6, 5/6, 1/2, and then -1/2, 1/2, -1/2.
For Q inverse or for what?
For the whole
T
thing.
sub beta?
No, for this whole thing.
Okay.
I'm just jumping straight to that. Let's just say that that happens to be right. The reason I want to do that is make sure that you guys can do the final step now. If this is my T sub beta, then let's go back to the schematic. If I want to find T of ABC, I write ABC like a column. Fine. Then I take the matrix that I just wrote down there and multiply it by ABC. So if I take T with respect to beta times a column ABC, what do I get? Well, I'm going to get 2/3 A plus 1/3 B minus C. It's okay. I'm just going to, I don't want to get too distracted. I just want to make sure, given this matrix, everybody can figure it out. The second row would be, what? 1/6 of A plus 5/6 of B plus 1/2 of C. And then the third row would be -1/2 of A plus 1/2 of B minus 1/2 of C. So that is the coordinate vector of T of ABC. Right? That's the coordinate vector of it with respect to beta, because we're using the matrix representation of beta. Beta being this nice basis. Right? So this is the coordinate vector, so these are just the coefficients. If I wanted to write what is T of ABC? Well, it's literally just this times 1, 0, 0, plus this times 0, 1, 0, plus this times 0, 0, 1. Which just means these three scalars are going to end up as the three components of the answer. This is going to be, our final answer is a vector in R3. So the first coordinate is, I'm literally just recopying this again, 2/3 A plus 1/3 B minus C, comma, 1/6 A plus 5/6 B plus 1/2 C, comma, -1/2 A plus 1/2 B minus 1/2 C. End of story. So it's correct modulo the problem with the matrix there that I probably have, but it shouldn't be too bad. Okay. You guys all right with that? Reasonable? Okay. By the way, I was earlier on, I was reading, I don't know if anybody's taken me up on this, but in the 250B book, section 5.11 on Jordan canonical forms, really worth looking at. I wrote this to be very readable, and it's not even really written for a, 300 level. It's more for 200 level. So if you go through this, it's hopefully would make some reasonable sense. Okay. Let's try one more example, which I'm actually going to pull out of that book. Is this okay? Okay, we'll try one more example, and then maybe there'll be a quick theoretical thing or two to ask you about. And then probably by 7 we'll be all zonked out, if we're not already. Okay, here's what I want us to do. What number am I on?
Six.
6. Only number 6? Jeez. Amazing how much time it can go by. Here's what I want us to do. Solve x1 prime equals negative 9x1 plus 9x2. And x2 prime equals negative 16x1 plus 15x2. It's a system of differential equations. So we're doing one of the, remember the applications, there are Markov processes, and then there's systems of DEs. So let's try a system of DEs, because it's been a little while since we've done this. What might you think about doing first here? Yeah, put it into a matrix form, right? Put it in a nice form. So the vector here on the left, right? I just call that x prime. I'm going to put an arrow on top of the x just to make it really clear. And then there's a matrix, and it'll be multiplied by x. What are the entries of the matrix?
No, 9.
9.
-16. 15.
There we go. Okay. So we get that little matrix like that. And so really this is just x prime equals ax. So you see a linear system and it's in that form. What do you need to do next? Okay, we need to take the matrix A and try to diagonalize it, find its eigenvalues, all of that good stuff. So let's do that. Let's take the determinant of A minus Ti. This would be the determinant of negative 9 minus T, 9, negative 16, and 15 minus T. Okay, so my numbers are not the smallest in the world. Negative 9 minus T, 15 minus T, and then plus 16 times 9 happens to be 144. So if we work that out, we're going to get T squared minus 6T, and then 15 times 9, oh goodness, 135, I believe. So negative 135 plus 144 is actually plus 9. So this actually gives you T minus 3 squared. T minus 3 squared. So what are my eigenvalues? 3 and 3. Always write down the repeats. If something's repeated, you should write it down as many times as is repeated. Okay. So what do we need to do next? Say again?
We have to find our vectors with the multiplication and
Right, so we're going to do the null space of A minus 3i. Exactly. We're going to find the corresponding eigenspace here. That means I need to subtract 3 from the main diagonal. So if I subtract 3 from the main diagonal, I'll get negative 12 and 9, and then I'll get negative 16 and 12. Remember that this matrix has to be not invertible because we're solving for the determinant to be 0, which means it's not invertible. So we can cross off one of these rows. And how many free variables am I going to have?
1.
Only one, right? Which would be this variable over here. Can anybody just by eyeballing it give me a vector that would be in the null space of that matrix?
3,
3, 4. I was going to say
9.
9, 12, but 3, 4 is fine. The point is that that is only one vector. And so this eigenvalue, which had an algebraic multiplicity of 2, produced only a one-dimensional eigenspace, so my matrix is not diagonalizable. Right? But can we write down the Jordan canonical form for the matrix already?